Today we're going to be looking at direct and inverse variation. So when we think about variation, what we're thinking about is what are the variables doing? So in direct variation, we'll have the equation y is equal to kx. And we again read that as y varies directly with x. So we can think about the fact that because we're multiplying by k, which is our constant of variation, as y gets bigger, x is also going to get larger. With inverse variation, so the opposite, when we think about inverse, we want to think about the word opposite. We're dividing that constant of variation by x, which means that our values for x are getting smaller. So as one of those, as x gets larger, actually y is going to get smaller because we're dividing. So the constant of variation is just a ratio that doesn't change between variables. So it's a given number that we can find based on the relationship that is given to us with the variables. So we think about with direct variation that our graph is going to be linear. However, it's important to notice here that we have a y-intercept of 0. So we can have linear functions that don't have a y-intercept of 0. We would not put those in the category of direct variation. Our graph for inverse variation is actually our family parent function that we call a rational function. You can also see it called a reciprocal function in some textbooks. And what we see here in the characteristic, again, we said that as x is getting larger, y is getting smaller. So we see that downward shift there of that curve. The x-axis serves as an asymptote for this graph, as does the y-axis. The y-axis is a vertical asymptote. It's a line that we're going to get really close to, but never actually touch. And the reason we have a vertical asymptote at the y-axis is because I can't plug in 0 for x. If I tried to plug in 0 for x and divide by 0, it's mathematically undefined. And so therefore we have a vertical asymptote on that graph. When we're solving these problems, we want to first create an equation based on how the problem is worded. So if they're telling us it's a direct variation, then we need to write that with multiplication. If it's an inverse variation, we would write that using division. You're going to substitute everything that's given to you, everything you know about any of the variables, and solve for k, the constant. And then you go back to the equation that you wrote. You again plug in the k value that you know and any other variables that are given, and then you solve the equation. And it can be worded different ways. They can ask you different things. Another thing or type that we need to know about is joint. So joint variation would be something that says that y is going to vary jointly with x and y, or excuse me, x and z. And so we're still using multiplication, but now rather than having a single variable, we're going to use multiplication with 2. So a lot of this type of problem is really just to know about knowing those relationships and knowing what to plug in for, and then being able to solve. We have some graphs, equations, and tables here. So we're going to determine if they represent direct variation. If they are representing direct variation, then we need to find the constant of variation. And then also write the equation. So for graph 1, we have a linear function. However, its y-intercept is not at 0. So anytime we have a graph, that's going to be the first thing that we want to look at. So this would not be an example of direct variation. For this equation, y equals 2x minus 1, we notice here that we have y equals 2x, which is an example of direct variation, but because our y-intercept here with our linear function is -1 and not 0. This would again not be an example of direct variation. In this table, what we want to look for is, do we have the same constant of variation, which with this one we're going to take by dividing y by x and see if we get the same number. So 8 divided by 4 is 2, 14 divided by 7 is 2, 20 divided by 10 is 2. So yes, this would be an example. The constant of variation is 2. That's what we just found here. So we would say that y is equal to 2 times x. So every time I doubled, that was what my y value was. In the next example, again, we're going to take our y value and divide it by the x value. So -2.8 divided by 2, 4.2 divided by 3, and 11.2 divided by 8. And when we take and divide those out, we get a 1.4, which again is the k value. So yes, this is a direct variation because that is always the same, and y is equal to 1.4 times x. So in the next one, d is equal to 60 times t. So again, direct variation needs to be that multiplication. So we have the multiplication. We have a y-intercept of 0, which means that yes, this would be an example, and we actually already have the equation. And then for this last graph, we're going to look for first to see that we have a y-intercept of 0, and then we need to find the slope. So when we found that constant of variation for those other examples, we were simply finding the slope. Remember that slope is rise over run, and this graph is just a little bit small, but here's a couple of points. So we're going up 1 over 2. So m is 1/2, and again, when we think about going to direct variation, that's going to be your k. So y is equal to 1/2 of x. That's your equation. The questions that you have for these are going to be written out kind of more as word problems, which is why we were looking at those steps up here before. So we're going to want to pay attention to how they're varying. So y varies directly with x. So the first thing that I know is that I'm using this equation. So if x is equal to -2 when y is equal to 8, we plug in for x and y based on what we're given in the equation, and then we would, or in the word problem, and then we would solve the equation. So I would solve by dividing both sides by -2, which means that k is equal to -4. Once we solve for -4, then we go to the second part of the question, which says, what is x when y is equal to 18? So we go back to our original equation. Y is equal to, but now we know that k is -4, and I'm solving for x, so we would divide both sides by -4, and so x is going to be -4.5. The weight of a plank varies directly with its length. So again, we can use some different variables. The weight is equal to, varies directly with its length. If an 8-foot plank, so that's the length, so we plug that in for L, weighs 32 pounds, so our weight gets plugged in for W, then how much would a 12-pound plank weigh? And what is the constant of variation? So we're going to solve for the constant of variation with the equation that we set up. Divide both sides by 8, which means that k is equal to 4. So if I have a 12-pound plank, we plug in the K, we plug in the weight, multiply those together, and that tells me that that is going to be 48 pounds. The number of words Tom types varies directly with the amount of time he spends typing. So number of words varies directly with the time. If he types 300 words, so that's W, in 6 minutes, which is T, that means that K is going to be equal to 50. 300 divided by 6 is 50. So how long would it take him to type 525 words? So we know that K is 50. We just have to solve for T. And 525 divided by 50 is 10.5 minutes. So you see we're using that same equation twice. We're just using it to solve for different things. And number 4 is an example of joint variation. So we're going to see the difference there. They're going to say it varies jointly with x and z. So y is equal to k times x times z. If y is equal to 16 when x is 5 and z is 2, so again we're just plugging in for everything that we're given. So that would be 10 times k, and then divide both sides by 10. So our constant of variation for this problem is 1.6. Then they want us to find y when we have x equal to 8, so I'm just going to plug in as I go. 1.6 is k, we solve for that, times 8 times 3, which when we multiply all of that together, y is going to be equal to 38.4. The other type of problem is inverse variation. So y varies inversely with x, which means we're using the division. If y is equal to 4 when x is equal to -2, so we plug that in, k is going to be equal to -8. What is x when y is equal to 7? So 7 is equal to -8 over x because that's what we're solving for. If I multiply both sides by x and then divide, x is going to switch with the 7, which means x would be equal to -8 over 7. The time it takes to travel a certain distance varies inversely as the average rate of travel. So again, t is equal to k divided by the rate because it's an inverse variation. Averaging 42 miles per hour, it takes Andre 5 hours. So 5 is t, 42 is r. 42 times 5 is 210. So that's k. If his last trip to the beach took him 4 hours and 20 minutes, so that's our time. Then we would need to change that to a decimal, so that would be 1/3 of an hour. 4.33 is equal to k over, not k, we solved for k. K was 210. We need to solve for r. So again, the r and the 4.33 are going to change places when we multiply and then divide. You need to see that algebraically. Multiply both sides by r and then divide by 4.33, which means his average rate of change was 48.5 miles per hour. In the next example, we see that the cost per person of renting a bus varies inversely. So the cost is going to vary inversely, so that's the division, with the number of people renting the bus. It costs $33 if 26 people rent the bus. So 33 for the cost, 26 for N. So we multiply both sides of that equation by 26, which means that K is going to equal 858. So the question says, how much will it cost per person if 56 people rent the bus? So cost is equal to 858 because we're going to plug that in for K. We have 56 people that will be attending, so our cost per person when we divide 858 by 56 is $15.32. The last type of problem we're going to look at is combined variation. So we have direct and inverse variation occurring at the same time. And so when we start to read these problems, it can get a little confusing and a little wordy. So we're going to start with looking at the first sentence. So it says that x varies directly with the square of y. So x is going to vary directly with y, but the key word here that we have to pay attention to is also that says squared. So I can't just have the variable y, I'm going to square it, and x is listed first, which means that one is going to be on the outside. And then they tell us that it's inversely related to the cube root of z. So I have to take, and in that denominator, put the cube root of z. So one thing to know about is that the order is important, and then also paying attention to some of these other operations because they can throw in some other things at you that we're not used to seeing. Number 9, the maximum load of a horizontal beam that is supported at both ends varies jointly as the width and square of the height. So we're going to start there with our joint, which is that multiplication. So the load, we'll use a capital L for that. K is the constant of variation as the width. And again, it's joint, so there has to be two things multiplied here, the square of the height. So H squared, and inversely as the length. So if it's inversely, division divided by L. And then we just have to start to plug in and solve. A beam 6 meters long, so that's going to be L, 0.1 meters wide, W, 0.06 meters high, H, supports a load, that's the capital L, 360 kilograms. So we're going to go ahead and plug in what we're given. We have everything except for K. And again, we have to make sure we square that 0.6. And then we're going to divide by the length of that beam, which was 6. So I've actually already worked all of this out on the calculator, but you would need to multiply 0.1 and then 0.06 squared. You can also start by multiplying both sides by 6 and then dividing by that. There's a couple different ways that you can do that, but K is going to be equal to 6 million. So kind of a large number there. And then the question says, what is the maximum load? Again, that was our capital L, supported by a beam 16 meters long, 0.2 meters wide, and 0.08 meters high. So again, we're just going to start plugging in for what we know. So we solve for K. So I plug in the 6 million. We know that the beam is 0.2 meters high. We know that it's 0.08 meters high, so we have to square that, divide it by the length of the beam, which is 16, and then again, I've already worked this out, but once you take and calculate that, it is 48 kilograms.